Okay, now that we've had a little practice with the applications of linear transformers, let's do a whole circuit analysis using the linear transformer model. So we've got a circuit, and it's going to have a voltage source of 245.2 volts, and it's got an angular frequency of 800 radians per second. We're going to have that voltage source have a series impedance of 184 plus J, 0 ohms, so purely resistive. It's then going to connect to the transformer. The series resistance of the transformer is on the primary side is 100 ohms. The self-impedance of the transformer on the primary side is 0.5 henries. That completes the primary side. The secondary side self-inductance is 0.125 henries. The series resistance is 40 ohms. And this transformer is going to feed a load that is a resistor in series with a inductor. That's 360 ohms in series with this inductor, as we said, that inductor having a value of 0.25 henries. We're going to have a dot here and here. Additionally, we know that the coefficient of coupling is 0.4. And for this, we want to find the reflected impedance, ZR. We want to find I in the primary side and I in the secondary side. So, very simply, for ZR, we can kind of fall back on our earlier circuit analysis. Omega squared M squared over R2 plus J omega L2 plus ZL, if we've got that circuit model, which we do. So we can just go ahead and plug and chug that one. The first thing that we have to know is M is equal to K square root of L1 L2. So we're just going to substitute that into the equation. Therefore, omega squared M squared over ZL plus R2 plus J omega L2 is going to be 800 radians per second squared times M, which is 0.4 times the square root of 0.5 times 0.125. So that whole thing is M. We square that. We divide by the load impedance, which was 360 ohms plus J omega L, so it's J times 800 times 0.25. We add to that R2, which is a little off the page there, 40 ohms, and then we need to add to it J omega L2, J times 800 times 0.125. And that's going to give us a value of the reflected impedance of 10.24 minus 7.68, or J 7.68 ohms. So the reflected impedance looks like a 10.24 ohm resistor in series with a 7.68 ohm capacitor. So now what we need to do is solve for the current in the primary side. Since we just solved for the reflected impedance, what we can do is we can redraw the above circuit model using the reflected impedance. That's going to give us the voltage source. We then have our 184 ohm resistor. We then have a 100 ohm resistor. We have the impedance of the transformer itself, which was 0.5 henries, or at least the inductance is. And then we need to include that reflected impedance, which we know was a resistance and a capacitor. And the resistance was 10.24 ohms, and the capacitor was minus J 7.68 ohms. Again, this voltage source was 245.2 volts. So I is therefore just equal to 245.2 at an angle of 0 degrees volts divided by 184 plus 100 plus J.5 times 800. That's the reactance of the primary winding, plus 10.24 ohms minus J 7.68 ohms. We don't have to convert that over. It's already a reactance from our calculation for the reflected impedance. This gives us a value of I is equal to 0.5 at an angle of negative 53.13 degrees amps. And then what we can do is we can go way back up in our notes, and we where did we write that? I know we did it someplace. Ah, okay. Here it is. Sorry about that. We see that I2 is equal to J omega M Z22 times I1. So we've got I2 equals J omega M over Z22 times I1. That is I2 is equal to J times 800 times M, which was 0.4 times the square root of 0.5 times 0.125. We need to divide that by Z22. Remember, Z22 is the total impedance of the secondary side, so that's going to be the impedance of the self-impedance of the transformer, J times 800, 0.125. We need to add to that the resistance of the secondary of the transformer, plus 40. And then we have the load device, which was plus 360 plus J times 800 times 0.25 to account for the inductance. And what that gives us is I2 is equal to 0.08 at an angle of 0 degrees amps. So that's how you use the concept of reflected impedance to kind of simplify circuit analysis. We could have, if we had wanted to, we could have just drawn I1 and I2 and used mesh current technique to simultaneously solve those. That would have worked too. That technique for solving the circuit would have worked just as well as the method of calculating reflected impedance. It's just that reflected impedance tends to be a little bit easier to calculate. So, we've demonstrated both methods now. Feel free to use whichever one you want to solve the homework problems. I'll do both methods in the homework so that you'll get plenty of practice with both.